The last topic I want to cover today is on linear transformations. This is from section 2.6 in the text. Um, we discussed transformations previously. We now want to focus on specifically linear transformations. Linear transformations have two properties. Um, the first property is that the transformation applied to the sum of two vectors is equal to the sum of the transformations applied to the individual vectors. That's one property. That's homogeneity. And then the other, also called the addition property, and then the other property is scalability, that the transformation applied to a multiple of a vector x is equal to that multiple applied to that multiple of the corresponding transformation of x. Equivalently, these can be combined into one property, that the transformation applied to a linear combination of vectors is equal to that same linear combination of the transformation of the individual vectors. AN. So these are, you can use either one of these tests to see if a transformation is linear. So all matrix transformations, matrix transformation is defined like this. All matrix transformations are linear. And correspondingly, all linear transformations can be represented as a matrix transformation, a matrix multiplication. Okay, before we proceed, let me define what's meant by the standard basis. The standard basis of a space, of a vector space Rn, is the set of columns of the identity matrix In. So this would be the set. We call these basis vectors E1, E2, and so on up to En. So these are just the columns of the identity matrix. So each one of these would have a 1 in the corresponding position. You're familiar with this concept. I think you've seen it certainly in 2 dimensions and 3 dimensions in your physics class. So the standard basis of R3, for example, would be the following vectors. 1, 0, 0. These all have, we haven't talked about length, but these all have unit length and are sometimes referred to as the unit vectors of the space. Often they're denoted, and depending on in statics, you might have called these I, J, and K. Sometimes they all are called E1, E2, and E3, depending on the textbook. Again, the standard basis of R2 are your x-directed unit vector and your y-directed unit vector. In that case, for R2, it's just the 1, 0 and the 0, 1 vector. What's important about the standard basis is that any vector in R3 can be written as a linear combination of the standard basis. And the representation is quite simple. It would be x1 times e1 plus x2 times E2. Indeed, these are often referred to as the coefficients of the standard basis representation. So here I'm just formalizing what you've seen before in 2 and 3 dimensions, and perhaps extending it to the n-dimensional case. Now, we've talked about finding the matrix of a transformation before, and we often just did that by finding the matrix and seeing that it satisfied a particular set of properties or satisfied the definition. We want to come up with a more formal approach. The matrix of any linear transformation is given by, the matrix of the transformation is, we just apply the transformation to each of our basis vectors in order, and then these form then give us the columns of the corresponding transformation matrix. Okay, so let's look at a couple of examples. One we've looked at before. So let's consider the transformation T, which is reflection about the x-axis. And I'm going to call this corresponding, following notation in the book, I'm going to call this corresponding matrix Q0, and we'll generalize the subscript in just a bit. So what I'm talking about here is, in 2 dimensions. So we'll look at the R2 to R2 case. Let's say this is V1. Actually, let me do it the other way. Say this is V1 with coordinate X and Y. So this is V1. And then the reflection of V1 about the x-axis, this is the x-axis, would be a corresponding vector V2 who's has the same x component but the negative y component. So for example, V1, it has coordinates x, y, and then the reflected vector by definition has coordinates x, y. The corresponding matrix of the transformation Q0 can be found quite simply, almost by inspection. In this case, 0 minus 1. We see that if we multiply this matrix times V1, that will produce this V2 vector. But now let's actually use this technique to get the Q0. So it says the transformation applied to our first basis vector. So E1 is just our x-directed unit vector, 1, 0. And similarly, E2, which would be, again, the second column of the corresponding identity, 2 by 2 identity matrix. Now apply this reflection about the x-axis to E1. That is actually E1. So E1 would be this vector has length 1. This is E1 along the x-axis. And if you reflect that around the x-axis, you get the same vector. Now E2, on the other hand, is our unit vector in the y direction, length 1. Reflect that around the x-axis, we get this vector, and this is actually the negative of E2. Okay. So what this theorem says is that the other way to get this transformation vector, this transformation matrix is it's just E1 and minus E2, or in other words, it's 1, 0 and 0 minus 1, which is the same vector or same matrix we got using that kind of inspection approach before. Let's look at another example. This is one that pops up quite often in computer graphics. We have a vector that we want to rotate by an angle theta. Okay, we're going to call the corresponding matrix R theta. And so what I mean here by this transformation, again, we'll look at the R2 to R2 case. If we have a vector V1 here, and then rotate that by an angle theta. Now, the convention is to take theta as being positive counterclockwise from the x-axis. So this is a positive value of theta in a counterclockwise direction. So V2 would have the same angle, but be rotated counterclockwise from theta. Okay, so by theta. Okay, so let's look at the corresponding rotation of E1 and E2. Okay, so E1 has unit length. This would be the corresponding rotated vector, has the same length. So this is the transformation applied to E1 through angle theta. And then the coordinates of the transform vector in terms of the x-coordinate and the y-coordinate. Along the x-axis, we just have, again, this has length 1, so that's the length of the hypotenuse. So the x-coordinate is just the cosine of this angle, cosine of theta. And then the y-coordinate here is sine of theta. This is the corresponding transformation of E1. So now let's look at the transformation of E2. It's a unit vector pointing in the y direction, okay. Increasing it by positive theta. Again, it has the same length, should have a length 1 here. Kind of not drawn that perhaps. But then the coordinates of this vector, again, this is the angle theta here. This distance is actually now the sine of theta. That's the, and it would be actually minus sine of theta because it's in the negative x direction. And then this distance, the y distance, is actually the cosine of that angle, cosine of theta. So the corresponding rotation matrix, R theta, would be cosine theta, sine theta from these components. And then from the transforming E2, the second column is minus sine theta, cosine theta. And then this is the corresponding transformation matrix. In the textbook, he uses shorthand notation for this, represents cosine theta just as C and sine theta just as S. So this simplifies some of the later notation. Okay. We've also looked at composite transformations previously. Where, you know, we let, starting in a k-dimensional space, applying a transformation T to produce a vector in an n-dimensional space, and then applying another transformation S to produce a vector in an m-dimensional space. And then we're going to let the transformation T be represented by matrix B and corresponding transformation S be represented by matrix multiplication by A. Then the composite transformation of S applied to T would be, first we're applying T, so that would be Bx, and then applying S after T, so that would be corresponding multiplication by A. So the corresponding matrix of the the composite transformation is the product of the individual transformations. The order is important here. So it's the matrix left multiplication first by the matrix corresponding to the first transformation, then left multiplication again by the matrix corresponding to the second transformation. This is a really powerful concept. In particular, it can greatly simplify finding these corresponding matrices of linear transformations. So let's talk about reflection about the line y equals mx. Okay, so what that would look like, and we'll look at this in 2 dimensions. So we have, this is the line y equals mx, so it has slope m. So let's take a vector v1 that is at this point. Reflection about the line would produce a vector of the same length, that's the same distance away from the line as v1, same perpendicular distance to produce v2. So this line here is perpendicular to our reflection line. So this is how v2 and v1 are related. And we're going to let qm correspond to this corresponding matrix transformation. You could probably, write down the components of v1 in terms of x and y, and go through a bunch of geometry and trigonometry to figure out what the corresponding components of v2 here are. Or, actually a little simpler would be the approach we've been taking, finding the components of E1, reflecting that about the line, and then do the same with E2, and then those would make up the corresponding columns of QM. We're actually going to take a different approach. Again, Q0 represents reflection about y equals 0. This is the x-axis. So if we let m equal 0, y is equal to 0 is just this axis. And we've already got the Q0 matrix. We found that in a previous example. Q0 was just 1, 0, 0, minus 1. Okay. So I'm also going to let theta be the angle between the line and the x-axis. So theta is this angle. Okay. Here's our x-axis. Here's that line. This is theta. Okay. So how is theta related to m? It's the rise over the run. So, or tangent of theta would be equal to m. So if I let this length be m, this length be 1, the corresponding hypotenuse here would be the square root of 1 plus m squared. So tangent of theta is equal to m, the slope of the line. This little triangle, though, makes it easy to also get cosine of theta, which would be 1 over square root of 1 plus m squared. And sine of theta, actually, let me write all those down. M is tan theta. And then we also have cosine theta is related to m. It would be 1 over the square root of 1 plus m squared. And then similarly, sine theta would be m over the square root of 1 plus m squared. Then I'm going to take a different approach to getting this QM transformation. So what I'm going to do is first rotate V1 by a negative theta. Now that would correspondingly rotate this line into the x-axis. Okay. So rotation first by minus theta of x. Okay. And then that would put the line at along the x-axis. And then if I rotate that vector or reflect that vector about the x-axis, and that's our Q0 transformation, that would have then the corresponding V2, but now rotated by a negative theta. I'm essentially rotating all the vectors and the line by negative theta, so the line is here. And then now I can reflect V1 above this x-axis. Then now I just have to rotate back. So I can write by theta. So I can write the corresponding matrix of this reflection about an arbitrary line as a product of three matrices. And I've already found all of these, right? So these are, for example, using my shorthand notation, cosine minus sine, sine and cosine. This is for the reflection about theta. Q0 we have as 1, 0, 0, minus 1. Reflection about minus theta, cosine of minus theta is equal to cosine of theta. Okay, but sine of minus theta is the negative sign. So the negative sign of a negative would be s, and then this would be minus s. Sine's an odd function and cosine's an even function. So actually if I carry out, so I can get this corresponding matrix by just carrying out this product of these three matrices. When I do that, I get c squared minus s squared, 2sc for this term, 2sc for this term, and then s squared minus c squared here. Okay. Now, I want to be able to express them in terms of m, but I've got that notation that allows me to do that in terms of the parameter m. This becomes 1 over 1 plus m squared, 1 minus m squared, 2m, 2m, and m squared minus 1. Okay. So instead of working directly with the vectors here, the work is simplified in this case by actually thinking of this reflection about this line as being a composite of three different transformations. And believe me, I think the math is quite a bit simpler. Probably should work through it, but I'm not going to waste your time to illustrate that this is a little easier than working directly with the E1 and E2 and reflecting them about the line. Okay, so that's it for the lectures today. I want to remind everyone we will have class on Wednesday. There will be lectures on Wednesday. I will not be posting lectures on Friday because that's our Easter break holiday. So, but that's it for today.